So good morning to all. So today we are going to discuss about a new topic, that is a stereochemistry of disubstituted cyclohexane. We have learned stereochemistry already in the BSc first year and second year. In the BSc first year, we have seen in the stereochemistry that stereochemistry is a branch of chemistry which deals with the study of organic compound by considering its three-dimensional model. And we have seen the stereochemistry of alkane, that is ethane, propane, and butane. We have seen eclipse form and the staggered form. In BSc second year, we have seen the stereochemistry of cyclic compound, Bayes chain theory, and we have seen the monosubstituted cyclohexane, and disubstitution pattern. So in TY, we are going to learn about the disubstituted cyclohexane, that is a one dimethyl cyclohexane. So let us see this point. So today we'll see stereochemistry of stereochemistry of disubstituted cyclohexane. Disubstituted cyclohexane. So you know what is meant by stereochemistry. Stereochemistry is a branch of chemistry which deals with the study of organic compound by considering its a three-dimensional model, right? So here we'll see about disubstituted cyclohexane. You know stereochemistry, right? In stereochemistry, stereo and chemistry, the chemistry of organic compound by considering its a three-dimensional model is called as a stereochemistry. And we have to learn about the disubstituted cyclohexane, right? So first we will write that is cyclohexane, that is a disubstituted cyclohexane. Here is a cyclohexane. This is your cyclohexane. And in the cyclohexane, you know there are the two hydrogen atom on each carbon atom. So you are having two hydrogen atom on each carbon atom. So I can write this H like this one. H, H, this also H, H, then hydrogen, hydrogen. So all carbons are having two hydrogen atom. So it is your cyclohexane. So it is, how many carbons are there? There are 6 carbon, and hydrogen, there are the 6 into 2, 12 hydrogen atom. So it is a C6H12. So this cyclohexane, when you replace the two hydrogen by a group like X and Y, so it is called as a disubstituted cyclohexane. cyclohexane. So here what we'll do, we'll write this cyclohexane, and this cyclohexane, you can replace the two group either from the same carbon atom, so it may be the same or different XY group. It may be from 1 2 position. Here is a X, here is a H, so here is a Y. Then it may be also from 1 2 position, then here is a 1 3 position. I can write here X and here is a Y, and one more compound, that is this one. Here is a X and here is a Y. So in this case, you'll see that they are at one position. So it is called as a 1 2 disubstituted cyclohexane. So they are at 1 and 2 position. So it is called as a one. It is a 1 1. First one is a 1 1, right? First one is a 1 1. So it is a 1 1 disubstituted. Second is a 1 2, because the two group X and Y, they are at 1 2 position. Third one is a 1 3 disubstituted, and fourth one is a 1 4 disubstituted cyclohexane. So it is the substitution pattern. It means when the two hydrogen atom from the cyclohexane is replaced by two substituent, then it is called as a disubstituted cyclohexane. So they are 1 1 1 2 1 3 and 1 4 cyclohexane, right? Now this is about the substitution pattern, and we have to learn about a disubstituted cyclohexane. So firstly, we'll take this 1 1 disubstituted cyclohexane, right? Now in this case, if you see, first example is 1 1 1 1 disubstituted cyclohexane. So when the two hydrogen from the cyclohexane is replaced by the two substituent from one position, it is called as 1 1 disubstituted cyclohexane. So here first point is the position, so from which we replace a group, right? So here position is 1 1 position, right? Position is 1 1. So from 1 1 position we replace the two hydrogen by the substituent, so it is a 1 1. Now here we'll write its structure, and let us see its stereochemistry. Now here, for writing the structure, so we have learned already in the BSc second year how to write down the structure of that compound. So here what you have to do, you have to write two line parallel, right? You have to write a two line parallel like this one. So one, right, and these are two. These are the two parallel lines, right? So I can then the length of these two lines is same, and they are parallel to each other. They are parallel to each other. Then this carbon is somewhat above, right? So you have to join this bond, right? You have to join this bond, right? So in this way you have to join. Similarly, this bond and this bond should be parallel, right? So here if I write this carbon here, then you have to join this bond, right? And this bond should be parallel, so you have to join this bond, right? So it is your cyclohexane, right? So in this way you have to draw the structure. How to use the numbering? Here you can write number 1, right? Here is a number 1, suppose number 1, number 2, number 3, number 4, number 5, and number 6. So it is your cyclohexane. In this way you have to draw the structure. So the bond 5 and 6 I have written elongated downward, and the bond 2 and 3, they are parallel to this bond 5 and 6. The length of bond 5 and 6 and the length of bond 2 and 3 is same, and they are parallel to each other. Similarly, the here the carbon number 1 is above the plane, right? And here the bond 1 2, right? The bond 1 2, this bond 1 2 is parallel to bond 5 4 or C4 C5. So these two bonds, they are parallel, means parallel bonds, they are parallel, opposite bonds, they are parallel, right? Similarly, bond number 1 6 and 3 4, they are parallel, right? And the length is again same. So in this way you have to draw the structure. So firstly we'll see the how to write down the bonds in this cyclohexane. We have learned already in the BSc second year how to draw the cyclohexane. So here, look here, carbon number 6, it will come and meet into the carbon number 1, right? Carbon number 2, it will come and meet into the carbon number 1. So 6 and 2, they are going to meet in the carbon number 1. So they are going up. They are going up, right? So if you see the model, the bond, the carbon 2 3 5 4, they are in the plane. That is the carbon number, right? Carbon number 2, then 3 5 and 6, they are in the plane, right? So the plane containing carbon number 2 3 5 6, so they are called as average plane, or general plane, so any two parallel carbons, they are in the plane. Similarly, we can say the carbon number 4 5 and 1 2, they are in the plane, right? So the opposite carbons, they are in the plane. So the plane containing the 4 carbon here, for example 2 3 5 6, it is called as a average plane or the general plane, right? So they are in the plane, they are in the paper, they are in the plane and they are in the paper, right? Now here we have to write the hydrogen atom on the each carbon atom. Now here, suppose if I take the carbon number 1, right, there are the 2 hydrogen, right? So the carbon number 6, it will meet into carbon number 1. Carbon number 2, it will meet into carbon number 1, and they are going upward. So yeah, how to draw a vertical line like this one, right? It should be perpendicular to this average plane. So this is a hydrogen, this is your hydrogen, and it is called as a axial bond. So the bond which is perpendicular to the average plane, they are called as a axial bond. So here in this case, we have seen the axial bond. Axial bonds are the bonds which are perpendicular to the general plane or the average plane. They are called as a axial bond, right? So in this case, we have written on the carbon number 1 the axial bond, right? The axial bond. So here you have seen that the axial bonds, right? The axial bonds are the bonds which are perpendicular to the general plane, to general plane, right? This means perpendicular to the general plane, right? Now on the carbon number 2, right? So this the hydrogen on the carbon number 1, so it is upward direction, it is above the plane. Similarly, the carbon number 1 will come and meet into carbon number 2. The carbon number 3 will come and meet into the carbon number 2, and it is going down. So you have to write down just a perpendicular line on the carbon number 2, right? So this is your, that is a axial bond. Similarly, carbon number 3, so you'll see that 4 will come and meet into 3, 2 will come and meet into 3, and it is going upward. So here we have to draw just a perpendicular line on the carbon number 3. So here it is on this carbon number 3, right? Similarly, carbon number 4, so it is going down. So you have to write down the perpendicular line on the average plane. Similarly, carbon number 5, so it is again just like this one, right? Carbon number 6, it is going down, right? So here this is the down, right? So in this cyclohexane, you will see that all are the axial bond. The hydrogens are the axial bonds. So how many axial bonds are there? There are 6 axial bonds, and out of 6, 3 are above the plane and 3 are below the plane. So 3 are above the plane and 3 are below the plane. So they are called as axial bond. So and they are perpendicular to the general plane. Right now, next one is a equatorial bond. Right, next is the equatorial bond. So in the equatorial bond, it seen that this equatorial bond, it uh, it looks coming out from the general plane, right? So here is a axial bond we have seen. Second number is a equatorial bond. So equatorial bonds are those bonds equatorial bond are those bond which looks coming out from the general plane. So it looks or looks coming from general plane or the average plane. General plane or average plane. Right? So it is your general plane. Right? Here is a general plane. Okay. Now we have seen the equatorial bonds. Now on the carbon number 1, again there is a 1 more bond, and this equatorial bond is parallel to, next to adjacent. Carbon number 1 and carbon number 6, they are the addition bond, right? So this bond is addition to the carbon number 1. So next to that one is carbon number 5 and carbon number 6, right? Carbon number 5 and carbon number 6. So you have to draw a line, so which is parallel to the C5 C6. So it is called as a equatorial bond. It is called as a equatorial bond, right? So these are the axial bonds and these are the equatorial bond. So this bond, equatorial bond, it looks coming out from the general plane. It looks coming out from the general plane or the average plane. So this is your equatorial bond, right? Now look here, on the carbon number 1, the bond written in the blue color, it is going up. So it is axial. So it is above the plane. So you'll notice that the equatorial bond will go down the plane. It will go down the plane. So axial bonds above the plane, then equatorial bonds it will go down the plane, right? So axial bond, they are above the plane, and equatorial bonds, they are the below the plane. So if one axial bond is above the plane, then other is below the plane. Now on the carbon number 2, so this is your axial bond. So it is down the plane. So of course the equatorial bond will go above the plane. So here this equatorial bond on the carbon number 2 is parallel to next to adjacent. So adjacent bond is which one? So C1 C2 is adjacent bond. So next to that one is C1 C6. So here just you have to draw a line parallel to your C1 C6, right? So C1 C6. So it is equatorial. So on the carbon number 1, you'll see that the equatorial bond will go down the plane. So on the carbon number 2, the equatorial bond will go above the plane. So similarly, on the carbon number 3, right? Check here. On the carbon number 3, the axial bond will go above the plane, right? Then equatorial bond go down the plane. It will go down the plane. So here it should go down the plane. Then you have to write down, it should be parallel to, next to adjacent. So which bond is adjacent? The bond C3C4 is the adjacent bond, and next to that one is C4C5. Means you have to draw a line parallel to C4C5. So here just you have to draw such type of line. So it should be parallel. So it is equatorial. Similarly, on the carbon number 4, so the hydrogen axial is down the plane. So you have to write down the equatorial bond, right? So tell me, the equatorial bond on the carbon number 4 should be parallel to which bond? Ankita, the carbon number 4, here is the carbon number 4, right? Here is the carbon number 4, right? So carbon number 4, This blue bond, it is axial bond. It is a perpendicular to the average plane. It is going down, right? Of course, the equator will go above the plane, but you have to draw the structure or the line equatorial bond. So it should be parallel to which bond? Yes, it should be parallel to which bond? Carbon number 4, equatorial bond. Anyone, you can tell me. Yes. Supriya Chaudhary. Supriya, on the carbon number 4, you have to draw equatorial bond, right? So that equatorial bond should be parallel to which bond? Srushti. Yes, yes. Supriya, yes, bolo.
Yes, 5 and 6.
5 and 6,
6.
right? Right, yeah, absolutely right. Look here. The carbon number 4 is here, right? And the addition bond is either C3C4 or either C4C5. These are the two addition bond. So you have to draw a line parallel to next to this two, means next to this two means either this 2 3 or 5 6, because both are parallel. So on carbon number 4 you have to draw a line parallel to, right, parallel to this C5 6 6. What you feel easy, that you have to check. So you have to draw a line parallel to this one, right, 5 6. So it is your called as equatorial bond, right? Similarly, on the carbon number 5, it should be parallel to. So 5 4 and 5 6, they are the adjacent, and next to that one is a 1 6, right? 1 6 or 3 4. So you can draw a line 3 4 or parallel to 3 4 or 1 6. Why? Because both are parallel. So just I will draw a line parallel to 3 4, right? So this is your 3 4, right? So in this way you have to draw such type of axial and equatorial bond on the carbon number 5. Similarly, on the carbon number 6, right, you have to draw the equatorial bond. So tell me, one of you, the equatorial bond should be parallel to which bond? Equatorial bond should be parallel to which bond? Huh? On the carbon number 6. On the carbon number 6, I have to draw the equatorial bond. So it should be parallel to which bond? It should be parallel to, yes. Also you can write down in the chat box also. So there the bond means the bond between the two carbons. Previously it was in the between 5 6. So here on carbon number 6, here this 5 6 and 1 6, these are the adjacent bond, and next to that one is 1 2, right? 1 2 or 5 4. So it should be parallel to, 1 2. So here you have to draw a line parallel to 1 2, right? So it is your called as equatorial bond, right? So here you see that on the carbon number 6, the axial bond is in yellow, it go down the plane. Of course, the equatorial bond go above the plane. So here, firstly, we should know how to draw the axial and equatorial bond. In this topic, this is very important. If you understand how to draw the cyclohexane and how to draw the axial and equatorial bond, then everything is easy, and everything is easy, right? So here we have drawn the structure of a cyclohexane. Now, position 1 1 dimethyl cyclohexane. 1 1 dimethyl cyclohexane means you have to replace the two group. Suppose this is your carbon number 1. You have to replace this two group by a group. Here I take X and Y, right? X and Y, right? X and Y. So it is a 1 1 dimethyl cyclohexane. It is a 1 1 dimethyl cyclohexane. This 1 1 dimethyl cyclohexane it undergo a ring flipping, right? It undergo a ring flipping. What is in by ring flipping? Ring flipping means the conversion of one chair form into the other chair form is called as a ring flipping. Due to the carbon-carbon single bond rotation, the one chair form convert into the other chair form is called as a ring flipping. So here it is a one chair form, and now it will convert into the other chair form. Let us see how to convert into the other chair form. So here you have to draw it's a mirror image just, right? So just you have to write down it's a mirror image. Look here, the carbon number 5 and 6 it go down, right? So similarly you have to write down the carbon number 5 and 6 it go down, right? So same thing I will write, right? So carbon number 5 and 6 it go down. So here is your 5, right? And here is your 6, right? Here is your 6, right? Suppose if I write here 6, here is a 5, right? And here is your 6 on this carbon, right? Just I have to draw a line. So this is your 5 6, right? 5 6, right? Not just I will draw near to this one. Elongated downward, right? It is elongated downward. So here is elongated downward, right? One bond. Now other the bond is parallel, right? So this carbon number 2 and carbon number 3 is again parallel, right? So it is your carbon number 2, right? And carbon number 3, they are also parallel, but they are having the same distance, right? So just I will draw again parallel line. The length of these two, they are similar. Similarly, carbon number 1 is above the plane, right? So here is the carbon number 1 is above the plane. Just you have to draw these two lines, right? Now carbon number 4. So carbon number 4, here it is a down the plane, but it is parallel to this one, right? So suppose if I write here uh, carbon number 4 is here, right? So this will go down and this will go down, right? So in this way you have to draw such type of structure, right? So again same thing, I will give the numbering. So it is your carbon number 1, and carbon number 1, then carbon number 2, carbon number 2, carbon number 3, carbon number 4, carbon number 4, carbon number 4, carbon number 5, and carbon number 6, right? So same thing I have written. Now firstly we'll write the axial bond. Axial bonds, in this case these are the red bonds, right? So this axial bond should be parallel to, that is average plane. So here it should be parallel to the average plane. So just I will draw a parallel line, right? So here is a parallel line. Okay, right? 1, carbon number 1, then carbon number 2. So here it should be parallel, right? Then it should be parallel, right? It should be parallel. It should be parallel, right? Then it should be parallel. So in this way, you have written the bonds which are perpendicular to the general plane. Here we will write the hydrogen atom. So the hydrogen atom, right? They are perpendicular. So here I have written in the red, right? So we should write in the blue, but no problem. Here we have written the red. So here is the axial bonds, right? Here is the H, right? Here is the H, H. Three are below the plane and three are above the plane, right? Three are below the plane and three are below the plane. H, and here is also H, right? Now we have tried the equatorial bonds. Now carbon number one. This carbon number one, it is a it coming out from the general plane or the average plane. So on the carbon number one, it should be coming out from the bond 5 and 6. You have to write down the parallel line, right? You have to write down the parallel line to the 5 and 6, right? So here is the 5 and 6, right? So carbon number 2, it should be parallel to 1 6 or 3 4. So 1 6 or 3 4, right? Look here, this bond and this bond, they are parallel, right? Now carbon number 3, it should be parallel to. So this bond is adjacent and this bond is the next one. So it should be parallel to carbon number 4 and carbon number 5, right? It should be parallel, right? Then carbon number 5, it should be parallel to 1 and 6. Here is a 1 and 6. And carbon number 6, it should be parallel to. So this bond is adjacent and next to that one is 1 and 2. So here you have to draw a line parallel to this one, right? So in this way you have written the axial and equatorial bond. Let us draw the hydrogen atom. So here you'll see that this hydrogen atom, they are this yellow bond, this red bond is above the plane. Then the equatorial bond will go down the plane. Carbon number 2, in the carbon number 2, you'll see that the red bond, axial bond, it go below the plane, so it go above the plane. Next one, carbon number 3, the red bond is above the plane, axial bond. So the black bond, it is equatorial bond, it go down the plane. Carbon number 4, the red bond is below the plane, so it go, that is the above the plane. So here we have to draw the above the plane bond, right? So here it should be parallel to, that is a 3 and 2, right? So in this way you have to draw this bond, right? So here is your hydrogen atom. Here is also hydrogen atom and a hydrogen atom. So in this way we have drawn the structure of this axial and equatorial bond. So in this topic only this point is very important, right? If you understand this one, means how to draw the structure of cyclohexane and their axial and equatorial bond, everything is very simple, right? If you know one, remaining all are same. If you know one, remaining all are same. So here we have seen the position is 1 2 position. So in this case, when the two hydrogen atom, when they are replaced by, that is here actually here we have written the numbering like this one, 1 2 3 4, but in the actual case the numbering in this case, right, you have to write in this way. Just wait here, I will write numbering first. Look here, this is your carbon number 1. Carbon number 1 will go down the plane, right? As it go down the plane, then this go down, means here is the carbon number 1. Here is the carbon number 1. So this 2 will go above the plane, means here is the carbon number 2. Similarly, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, right? So this is the numbering, means when ring flipping takes place, of course, here what you have written, here we have written the mirror images, but in this case you'll see that the carbon number 1 will go down the plane. So here it is below the plane. In the previous case, in the chair form, it was above the plane, right? So these are 1 dimethyl cyclohexane. Now you know how to draw the structure. It undergo ring flipping. Look here, the hydrogen number, the X on the carbon number 1, right? The X on the carbon number 1. In this case, the X on the carbon number 1, right? It is above the plane. So when it undergo ring flipping, then the it will go down the plane, right? It will go down the plane. So here the hydrogen will go, or X will go down the plane. Means here is X and here is a Y, right? Here is a Y. So the X group will go down the plane, right? So in the previous case, it was axial, right? But it will go equatorial, not here, it will go equatorial. So here it is X. It is X, means it becomes equatorial. It becomes equatorial. It becomes equatorial. And here is that is, this is your axial, right? So here Y is axial. In this case, Y is axial. Now in the previous case, the X was axial. When ring flipping takes place, it becomes equatorial. So axial bond becomes equatorial and equatorial bond becomes axial. So X was axial, it becomes equatorial. In the previous case, Y was equatorial, it becomes axial. Means the conversion of axial and equatorial bonds takes place. So axial bond becomes equatorial and equatorial bond becomes axial when it undergo a ring flipping. So it is called as a ring flipping, right? So here it undergo ring flipping and you get such type of two structure, structure number 1 and structure number 2. So here I may say the structure number 1 and structure number 2, right? So here is structure number 1, right? And here is a structure number 2. It is undergo ring flipping. So here what you have seen, we have seen how to draw the cyclohexane, right? How to draw the cyclohexane. We have seen how to draw the cyclohexane. The bond 5, 6, it go down the plane, elongated downwards. To this 5, 6 bond, you have to draw a line parallel. 2, 3, it is also parallel to this 5, 6 and it is also elongated downward. The length of this 2, 3 bond is somewhat downside, is somewhat more, right, towards the right side than this 5, 6. So the carbon number 1 is above the plane. So just you have to draw a line joining 1, 2 and 1, 6. Similarly, the carbon number 4 is below the plane. So you have to join the bond 5, 4 and 3, 4. So the carbon, the plane containing 4 carbon, opposite carbon, 2, 3, 5, 6, 2, 3, 5, 6. That plane is called as a average plane or the general plane, right? So that plane is called as a average plane or the general plane, right? And the bond which are perpendicular to the average plane or the general plane, they are called as a axial bonds. They are called as a axial bonds. So here these bonds are perpendicular to the general plane or the average plane. Similarly, equatorial bonds means these bonds looks coming out from the general plane. Here if you take the general plane 5, 6, then 2, 3, so the bond 1 on the 1 there is a 1y, this bond is equatorial. It looks coming out from the general plane, there is a 5, 6, 2, 3. So they are called as a equatorial bond. They are called as a equatorial bond. So it is your equatorial bond, right? So here you have seen the concept of axial bond and equatorial bond, right? And when it undergo ring flipping, the carbon number 1 will go down the plane and carbon number 4 will go above the plane, right? So here when it undergo ring flipping, the carbon number 1 will go down the plane and carbon number 4 will go above the plane. So here you'll see that in the previous structure, carbon number 1 is above the plane. So here in the second structure, carbon number 1 is below the plane, right? Similarly, the carbon number 4 in the structure number 1 is below the plane. So in the structure number 2, it will go above the plane. And also you'll notice that the axial bond becomes equatorial and equatorial bond becomes axial. So on the carbon number 1, there is a X group. So this X will go in the equatorial when it undergo a ring flaving. So here this is your 1,1 disubstituted cyclohexane. 1,1 disubstituted cyclohexane. Once you know how to draw the structure, remaining points are very very easy, right? They are very very easy. So in this case, first point, what you have learned, we have learned first point is your position, right? Position of this one, right? Here we have seen the first point is the position. What is the position of the two group? Here position is 1,1 when the two groups from from the cyclohexane, when two hydrogen from the cyclohexane, they are replaced from 1,1 position, so it is called as 1,1 dimethyl cyclohexane. So here the position is 1,1, right? The position is 1,1, right? Number two, you know the geometrical isomerism, right? You know the geometrical isomerism, right? Geometrical isomerism. What is meant by isomerism? Isomers means these are the compounds which are having the same molecular formula but same structural. They do not have the same structural formula, right? So they are called as isomers, and this phenomena is called as isomerism. Now here in this case, in the structure number one and structure number two, whether this 1,1 they are the geometrical isomers or not, you have to find out, right? Now in this geometrical isomerism, when you learn in the cycloalkane, you have to check whether it contains any elements of symmetry or not, right? Whether it contains elements of symmetry or not, right? As here in this cyclohexane, you have to check whether these two groups, right? Geometrical isomers means cis trans isomer. Geometrical isomers means cis trans isomer. If the two similar group they are on the same side of the carbon carbon double bond, they are called as a cis, and when they are on the opposite side, it is called as a trans. So cis isomer and trans isomer, it is a present in the alkene which contains carbon carbon double bond. But in this case there is the absence of the carbon carbon double bond. So what you have to see, we have to check whether the two groups they are on the same side of the average plane, general plane, or they are on the opposite side. So here you'll see that as the two groups both are same, right? X and Y, if they are same or maybe different, but you'll notice that here the average plane 2, 3, 5, 6, these are average plane. So here you'll see that the carbon number one is above the plane, it is above the plane, and in the section number two the carbon number one is below the plane. Means in the section number one the two group X and Y, if they are same or maybe different, they are above the plane or they are the below the plane. So here in case of 1,1 dimethyl cyclohexane, we cannot explain geometrical isomerism, or we can say that they don't exhibit geometrical isomerism, right? Why? Because the substituents are on the same carbon, right? So such compounds do not show that is the geometrical isomerism, right? So here as the two groups X and Y they are on the same carbon, so they don't show the geometrical isomerism, right? So this is about the geometrical isomerism, right? The next point uh, that you have learned is conformational isomerism. Conformational isomerism. Conformational isomerism. What is meant by conformational isomerism? Conformational isomerism means these are the isomers which can interconvert into each other. They are called as a conformations, and the isomerism is called as a conformation isomerism. Now look here, in the structure number 1 and structure number 2. Structure number 1 can be converted into structure number 2, and structure number 2 can be converted into structure number 1. So due to ring flipping, the conversion of 1 into 2 and 2 into 1 can take place. That's why they are called as a conformational isomers. They are called as a conformational isomers, right? So here, if structure number 1 convert into 2, in structure number 1 x was axial, and in the structure number 2 x was equatorial. So we can say that the structure number 1 and structure number 2, right? Structure number 1, right? The structure number 1 and the structure number 2, these are the conformational isomers of each other, right? So I can say that 1 and 2, these are the conformational isomers of each other, means it exhibit, that is the conformational isomerism, and 1 and 2, these are the conformational isomers, right? Now next point you have to see, that is a optical isomerism, right? Optical isomerism. You know what is meant by optical isomerism? Optical isomerism, right? What is meant by optical isomerism? Optical isomers means these are the isomers which have ability to rotate the plane of a plane polarized light is called as a optically active compound. And if it rotate towards right, it is called as a dextrorotatory, and if it rotate towards the left, it is called as a levorotatory, right? So here, which compounds it show the optical activity? When it contains asymmetric carbon atom, or if there is absence of elements of symmetry, is called as a optically active compound. It is called as a optically active compound. So here, for the optical isomerism, we have to check, right, whether they exhibit optical isomerism or not, right? So here in this one, right, so here if you see, right, if you see this compound, right, we can pass a plane, passing from carbon number 1 and carbon number 4, right? We can pass a plane from carbon number 1 and carbon number 4, right? So here just I will take such type of color, right? So here in this case, a plane passing from the carbon number 1 and carbon number 4, right? This plane is passing from the carbon number 1 and carbon number 4, right? Right? So a plane passing from the carbon number 1 and carbon number 4. So this plane is passing from the carbon number 1 and carbon number 4, right? So here you see that if both groups are same, X and Y, in that case, if both groups are same, X and Y, when they undergo ring flipping, right? When they undergo ring flipping, right? So you'll see that X is above the plane. Then in the other case, X will go down the plane. But if both are same, then XX means one is above the plane and other is below the plane. In the structure number 2 also, one is above the plane and other is below the plane. Means in this case, if both groups are same, we cannot write its optical isomerism, because it contains plane of plane, here it contains plane of symmetry, right? So if both are same, X and Y, suppose if I say same, X is X, so it contains plane of symmetry, means it do not exhibit a geometrical isomerism. But if X and Y, they are different, then it show geometrical optical isomerism. It show the optical isomerism. So in this case here, this we can write, if you X, right, and this Y, right, if they are same, right, if they are same, right, then it do not show geometrical isomerism, right? But here, if X, right, and Y, they are not same, right, then it show geometrical isomerism. Why don't show the geometrical isomerism? Because it contains a plane of symmetry. It contains a plane of symmetry. Just you have seen how it show the plane of symmetry, right? So a plane passing from the carbon number 1 and carbon number 4, it divides into two equal parts if they are same. Then if it contains any elements of symmetry, it don't show optical isomerism. But if x and y they are different, then it show the geometrical isomerism. So one position, two geometrical isomerism, three conformational isomerism, four optical isomerism, and fifth point, last point, that is the stability, right? So stability of this two conformation. So we have to see stability of this two conformation. Stability can be explained in terms of energy, right? Stability can be explained in terms of energy, right? So here, if you see energy of this two compound, lower the energy, right, more is the stability. Lower the energy, more is the stability, right? And if you see higher the energy, then lower is the stability, right? Now in this case, you have to check the stability of this compound. Here, if you see in this structure, you will see that x and y, if they are same, then you see that x is above the plane and x is below the plane if both are same in the structure number 1. In structure number 2, also if both are same, x is above the plane and x is below the plane, means they are having the similar stability. If both are same. But if x and y they are different, So when x is at axial position, so it have the interaction with the bond, hydrogen bond on the carbon number 3 and carbon number 5. So there is interaction between these two, right? They undergo interaction with these two, right? So it is called as a 1,3 diaxial interaction. But if a Y group is equatorial, it is away from the plane. It is away from the structure. There is no interaction. So in this case, we can make a general statement that in X and Y, a group which is a bulky, right? If it is in the equatorial position, that is found to be more stable. And so in structure number 1, suppose Y is a bulky group. If it is equatorial, it is found to be more stable. But in structure number 2, if Y is a bulky and if it is the axial position, it is found to be less stable. So we can make a general statement that, so here, in case of stability, if the both groups X and Y, right, if they are same, then they are having the same energy. Why same energy? Because both are same. In both cases, structure number 1 and structure number 2, X is axial, also X is equatorial. Similarly, so here they are having the same stability. Right? It means the same stability. Right? Same stability. But if the X and Y they are different, right? If X and Y they are different, right? So if X and Y they are different, then they are not having the same stability. So a bulky group, if it is in the equatorial position, right? If the bulky group is in the equatorial position, so it is found to be more stable. So we can say that bulkier group in equatorial position is found to be more stable, right? So it is found to be more stable, right? So between these two, you have to check which group is bulky. Means suppose, for example, one is methyl and other is hydrogen. Methyl is a bulky group. So when methyl is in the equatorial, it is found to be more stable. Suppose if you are having methyl and ethyl, if ethyl is in the equatorial, it is found to be more stable. So in this way, you have to check the stability. So in this case, only we should know the structure of this cyclohexane, Then you have to write down the axial and equatorial bonds, right? You have to write down the axial and equatorial bonds, right? And if you know how to draw axial and equatorial bonds, then we should know the that is the position of this bond, right? We should know the position of the bond, right? We have seen what is in by Everest plane, what are the axial bond, what are the equatorial bond, how to draw the axial and equatorial bonds, how many axial bonds are there, how many equatorial bonds are there, how many axial bonds are above the plane, how are they below the plane. So here there are the six axial bonds and six equatorial bonds. Out of six, right? The three are above the plane and three are below the plane. And then we have to explain the stereochemistry of 1,1-dimethyl cyclohexane. So if the two hydrogen from the cyclohexane is replaced by the two group, then it is called as 1,1-dimethyl cyclohexane. Geometrical isomerism, as in this case, the two groups they are on the same carbon, so we cannot explain the geometrical isomerism. Why? Because either they are on the upper side or on the lower side, so we cannot explain the geometrical isomerism. Conformational isomerism, yes, they can show the conformational isomerism. They are having two conformational isomer, 1 and 2. So 1 can convert into 2 and 2 can convert into 1. So they are having the two conformational isomers. Then about the optical isomerism, here we have to see whether it have any elements of symmetry or not. If it have the any elements of symmetry like a plane of symmetry, then center of symmetry, alternating axis of symmetry, center. So if all symmetry are absent, then there should be optically active. So here in this case, if x and y they are same, then it's seen that it have the plane of symmetry passing from the carbon number 1 and carbon number 4. So it divides this molecule into two equal half parts, and it have the plane of symmetry. So it divides this molecule into two equal half parts. So it have the plane of symmetry. So when it have plane of symmetry, it is an optically active compound. And here, if x and y, if they are not same, then in that case, it do not show any elements of symmetry, means it is an optically active compound. And about the stability, here, you know, more the energy, less is the stability, and less the energy, more is the stability. So here, in this case, if you see, if both groups are same, x and y, in that case, one is axial, other is equatorial in both structure number 1 and structure number 2. So they are having the same energy, means same stability. But if the groups are different, then if the group, bulkier group, if it is in the equatorial position, there is no interaction with the other group atom. So here there is having a less energy, means more stability. So with this point you have to learn, one is the position, second is the geometrical isomerism, third is the conformational isomerism, fourth is the optical isomerism, and fifth is the stability. So in this way you have to learn the remaining point. So here first point, very important point that one must know, that is the structure, how to draw the structure. These two cyclohexane, you have to draw the two cyclohexane, and you have to know how to draw the equatorial and axial hydrogen atom. We have also learned this point in the BSc second year, right? So in this way, we have seen the, that is how to draw the cyclohexane and the stereochemistry of 1,1-dimethyl cyclohexane. A question of 2 mark, 1 mark, they may ask, 1,1-dimethyl cyclohexane do not show geometrical isomerism. You have to draw both structure, and you have to tell that the two groups they are directly attached to the same carbon, so they can not show the geometrical isomerism. Why? Because the two groups they are above the plane or below the plane, right? Number 2, here 1,1-dimethyl cyclohexane, if both groups are same, then it is optically inactive, don't show optical activity. Why? Because it contains a plane of symmetry. And if both groups are different xy, then it don't show any elements of symmetry, it is a optically active. What is about the stability? Stability means here, if x y, if they are same, then they are having the same stability, means structure number 1 and structure number 2, they are having the same stability. But if the groups are different, if x and y are there, then if a bulky group, a big group, if it is in the equatorial position, that structure is found to be more stable. That structure is found to be more stable. So a bulkier group which is in the equatorial position, it is away from all type of the interaction. If the group is in the axial position, there is a presence of interaction between the hydrogen atom on the carbon number 1 and carbon number 3. This interaction is called as 1,3 diaxial interaction. And for 1,3 diaxial interaction, you have to add 0.9 kilocalorie per mole energy. Means here, if there's a more 1,3 diaxial interaction, more energy and less stability. Or we can make a general statement that if the group is in the equatorial position, there is no interaction, less energy, more stability. And so here in this way we have seen only one, that is a 1,1 dimethyl cyclohexane. Here we are going to learn only dimethyl cyclohexane stereochemistry. We are not taking the two group different. We are taking only the two group. They are similar. And again, there is a methyl group. So we have to remember number 1 point, structure of cyclohexane. Number 2, how to write down the axial and equatorial bonds. Number 3, ring flipping. Now, if you know this one, then next point, position, from which carbon we are going to replace the hydrogen atom by the methyl group. Then number 2, after position, you have to go for the geometrical isomerism. Either it shows cis or trans isomerism. If the two groups they are on the same side, cis. If they are on the opposite side, it is a trans. And then next one is a after geometrical isomerism, there is a conformational isomerism. Conversion of 1 into 2, 2 into 1 takes place. So they are the conformational isomerism. And next one is the optical isomerism. If it contains any elements of symmetry, it is found to be optically inactive. If don't have any elements of symmetry, it is optically active. And last point is the stability of that compound. And so if the bulky group is in the axial, it is a more unstable because having the more energy. If the big group, bulkier group, it is inside in the equatorial position, there is no interaction, it is away from interaction, then it is found to be more stable and less energy, right? So in this way we have seen 1 point, the stoichiometry of a disubstituted cyclohexane. Try to read at home, right? If you read today only, then it becomes easy to understand the concept, and everything depends upon each other. Whatever point we have discussed today, if you understand, if you know how to write a cyclohexane, remaining topic is a very easy. You can understand very easy, right? Remaining points. So make your concept clear. And I told you you can refer Manali publication or Nirali publication or organic chemistry by Morrison and Boyd or organic chemistry by Claydon, right? So these are some references that you can use, right? So if you in doubt, you may ask. If you in doubt, you can ask any question. Yes, Aniket. Aniket in doubt. Ankita. Ankita Verma. In doubt. Yes. Ankita Verma. Supriya Chaudhary. Supriya Chaudhary in doubt. Right. Okay. Then yes. Then no doubt. So try to read at home. Right. If you're in doubt, you may ask. Right. So I think we should stop here. Right. Thanks to all. You can leave the meeting. Thank you.
Thank you,
Thanks to
sir.
all. Thank you.
Thank you, sir.
Thank you. Thank you. Thank you.
Thank you, sir.
Thank you. Thank you. You can leave the meeting. Thank you.